In the last video, we ended with this slide that shown a new recognition pipeline, which is now defined by a neural network. So now we have the image and as the input, and then as the output we have a classification result. And this is achieved by using a neural network. So I'm going to show you how we go from shallow methods, that mean methods that are defined that are not deep, to deep methods. So in machine learning in general, what we want to find, being really rough here, so it's a general idea, is a function in the form f of x equals to y. The meaning of those f, x, and y are dependent on the task we have at hand. So let's say we have an image classification, as we are discussing, and what we have is data available, that means pairs of images and labels from desert, beach, and mountain. In here I included yet another class. In the previous video we discussed just desert and beach because there were two classes, easier, but we can define more classes if we need. The input is an RGB image in the form of X. This means I'm going to define that as a vector or as a matrix, for example. And the output is the predicted label, for example mountain, but it could be desert or beach, assigned to that input image. So it is basically a mathematical function. So what we have is x, we have y, and then f is responsible to take us from x to y, the input to the output. So this is the basics of machine learning in general. So what we can change that. We can change the task and then see f, x, and y in a different way. So let's say we want to perform anomaly detection in credit card transactions. In this case, the data available are legitimate transactions from a given client. And then the input is not an image here. Those are real valued data, including the transaction, transaction location, the currency, the value of this transaction, the timestamp, and everything will be in the form of x. So I'm going to use a vector with those values. It can have a dimensionality. In this case, if we have just location, currency value, and timestamp, it is 4. So we are working on 4 dimensions. And then the output is the probability y of observing a fraudulent, that means an anomalous transaction. See that now we have f. F will take us from this 4-dimension vector into a probability. It is also a problem that can be solved by machine learning, but we are now seeing it in a different way. So machine learning is a broad area that includes deep learning. In machine learning, algorithms aim to infer f, the function that I just described, from a space that is the input space x to a space that we call output space y. The algorithms are responsible for finding f, selecting from a space of admissible functions. The admissible functions are functions from let's say a set that we are going to draw. One of the functions that we can use, for example, are all linear functions. So when we say that a method is a shallow method, often what we are saying is that it infers a single function f that does this task of going from of being a map from x to y. For example, a linear function. So if we define a linear function, it has this form. So if I have just x is one-dimensional, so just one scalar, what we would have is that f of x equals to w times x plus b. So to perform machine learning, is to find values of w and b. Why? Because we know x. What we just have to know is which value to multiply this x with and which one to sum, so that we have y in the output. So it's basically a linear transformation. Examples of algorithms that work basically in that way are the perceptron, the support vector machines, the logistic regression classifier, and the linear discriminant analysis. So very famous methods that can be very effective and that are very simple in fact. And deep learning, how deep learning goes into that? So deep learning involves learning a sequence of representations via composite functions. So given some input x1, instead of directly going or learning a function f that takes this x1 and transforms it into a y output, we are going to learn a series of functions that have some hierarchical structure. So one function depends on the other function. In here, x1, which is the, let's say, the image or the original vector with the features, serve as input to a function f1, which will output x2. So we don't have here y, we have an intermediate representation. x2 is then used as input to f2 that outputs x3. x3 is used as input to f3 that outputs x4, and so on until we reach y. The output is achieved by several L-nested functions in this form. This is usually for this is a more restricted scenario, because this assumes that learning is sequential. It is not often the case, right? It's not always the case, but in general we can write with this type of in this form to make it simple. But in here I'm specifying a little bit more, because every function fi has a series of parameters that are associated with each function. So this theta, capital theta here, includes all parameters required to train, or to not to train, but to transform x1 into the output x2. So there are those nested functions here, is what we call deep learning. It is debatable if, for example, by learning just 2 functions, this is sufficient to say that we have deep learning. This is because there is a famous classification algorithm called multilayer perceptron, which in its classical version has 2 functions. It learns one function from the input to what they call hidden layer, which is an intermediate representation, and then finally a classification layer. But it can have more than that. So let's say if we have a neural network with 2 layers, is it sufficient to call it deep learning? Well, I'm not the one that will give you an answer to that. But what I say is that usually what we call shallow is just one transformation. But because we have currently networks that have hundreds of layers, sometimes when we use just a couple of layers, or maybe up to 3 or 4 layers, people will call that shallow. Remember that 8 years ago we were talking about a deep network with just 9 layers, and nowadays 9 layers are considered a very small number of layers. So anyway, let's say that we first want to learn a shallow linear classifier. Let's start with a shallow approach. So our input is an image that I'm going to organize in the form of x, as we require for in machine learning in general. And let this theta contain a matrix W of weights and a vector B of bias terms. I'm going to define both later, okay? So don't worry. So those are the parameters that we want to use to transform it. How are we going to transform X? By multiplying X with this matrix and then summing the bias here. This is just was designed just to make this in a fine transformation. So it's basically will perform a linear combination of all pixels in the image, and our output is going to be scores for possible classes of X. Let us take this example. So the input is an image with n by m by 3 numbers, 3 because it's RGB, that is vectorized into a column X. But here, to show in a single slide, I'm going to use just one slice, so just one matrix. And this matrix is a 2 by 2 matrix. I know this is not even, you cannot even recognize anything by just using 4 pixels, but bear with me and let us use this just as didactical example. So let's say that this image has only 4 pixels, right? So a 2 by 2 matrix. I'm organizing it in a vector. So we take the first pixel 1, the second pixel 73, the third pixel 227, the fourth pixel 82, and then this is the vector. And then I'm going to pass this X to a function f that with those parameters are going to output S, which are 3 numbers with class scores. Which classes? Now I changed here to another domain, so let's say that we have 3 animals, cat, turtle and owl. Then those are on the order here. So when we perform the multiplication Wx and then sum B, the output is those class scores. Recognize here, as you can see here, this is the image. So 173, so on. This is the image, so this is X. As you probably note, this is W and this is B. And those are the output scores. That means that by using those matrix and bias terms, what we have is a score of minus something here, and plus something here. So probably this is the correct class, owl. So what those means, well, I'm not sure. I'm going to talk about that later. But how do I come up with those values here? I know that the image has those pixels, so those are the actual pixel values. So those I know for sure. But what about B and what about W? Well, let us say, how can we choose that? Well, we start with random values. Yes, you heard correctly, random values. I'm going to start with just random matrix of weights and a random vector of bias, and then see what happens. In this case, I got, well, those results. Let's see we apply that with more images. So I just input this image, those 3 images, and then see the scores. For example, for this image, the score of owl is 460, which means, yeah, this is a high score. The classification was good. For this one, cat was 380, and the other one's lower, so yeah, okay. And for this turtle, as you can see here, the classifier is more confused. It assigned an hour here with a score of 26, but this score is not that high. So this means that we can improve that. Also, something that we can improve, that I'm going to talk later how to do that, is those numbers. Those numbers don't mean much, right? What does it mean to have a score of 460 or 60 or 26? This is can be elusive, so we're going to work on that in a bit. So what we need now in order to improve that, or to because remember, we started from random values. We want to improve that. We don't want to have random output, right? So we need a loss function that quantifies undesired scenarios in the training set. I use this term loss function because this is often used in the literature. So loss is something that we lose. So what this function will code what are we losing when we choose specifically that parameters. Which parameters? W and B. So the higher this function is, the worse we are. The lower the function is, the better we are. And we also want an optimization algorithm to find a set of parameters so that this loss function is minimized. So what we have here now is an optimization problem. So an objective function, in this case is a loss function, so we want to minimize that. And then, as I said, we want to optimize some function to select the best classifier, the best model. This is often called loss or cost function. And in theory, what we want to minimize is this. Don't be scared. Let us just delve into that and understand. So this is the expectation of the loss. So expectation of L, given the function, the loss, the function that we just used to infer the classification. This function will operate on x and y, and those are capital X and capital Y. Why I'm emphasizing that? Because x, because it's the expected loss, S is composed of all possible input data, and Y of all the output data. This means I have to sample, let's say, infinite, in some cases infinite possibilities. So if I'm using images, that means that we want to have X that is composed of images from cat that with all possible pixel configurations that will resemble a cat, and all possible pixel configurations that will resemble a turtle, and so on, and all Y's that are related to that, so the label. This is basically an integral of R over, in this case, the dimension of X and Y, of the loss function itself. However, this probability, so the probability of X and Y, we call that a joint probability distribution, is unknown. Why the joint probability distribution is unknown? Because we don't have access to all the examples. We cannot know that. For some problems we do know P of X and Y. For example, the probability of, let's say, we roll a die, and the number that we have is a prime number. So for this case we have all the probabilities, but for images we don't have. So how can we compute that if we don't have access to the expected loss? So let xi, yi be a training example. What is the training example? So it's one image that has a label that was assigned by a human, and f, a map that goes from x to y, a prediction function that uses parameter theta. We know that, right? So we can compute an empirical loss. An empirical loss for that example I is a function in the form L of f theta, which are the parameters, xi, yi. So can I know just the loss of a single example? Yes, I can do that. I cannot do it for the whole space, but I can do for one of them. And this is what we call the empirical loss. It's an estimate. It's not a perfect one, but it's the one that we have, and the one that we need, in fact. I'm going to conclude by showing you two typical losses. The first one is the squared loss that often operates on continuous values. It operates on the outputs, so the labels. In green here we have the predicted label, so the label that was predicted by the classifier, and in blue or purple is the true label. That means the label that we know that there is a true label. What is the point of comparing if I know the true label? Well, I'm going to use that, remember, I'm going to use that to minimize the function. I'm going to use that for the optimization. So I'm actually using the data that we know the labels for to find the parameters for future data. And another loss function that is very common nowadays to use is what we call cross entropy. Usually it operates over bits or probability vectors. It's basically an entropy, so an entropy value, but between the true label log predicted label, and 1 minus the true label log 1 minus the predicted label. So true label, predicted label. Sorry. Why is that? Because depends on, in this case, it depends if we have a positive or a negative class in here. So we're going to describe that better. But on the top one, it's easy to understand that the highest, the higher is this difference squared, the worse we are, right? If we have a perfect one, so we have 0 here. So 0 squared is 0, so the loss is 0. We have perfect prediction. So if the predicted label is very far from the true label, then this has become large, and then we are not that good. And here is the same. Okay, so the larger the similarity, the more similar we have the probabilities, the lower will be this number. And then we want to reach a classifier that would do this, something like this, that can separate all examples from one class to all the others, and so on. Note that now we have one classifier per class, because with, let's say, a linear classifier, the only way I can do is to measure if something is below or above the line. So I have to train one linear classifier per class in this case. Alright, so this is the basics for in which we're going to build our neural networks to do that. But we want to I want to emphasize that this is the basics for every optimization based algorithm that includes most of the classification algorithms that are available in the machine learning literature. So in the next video we are going to talk about how can we actually optimize that function and more. So see you next video.